So right off the bat, I want to mention that I made a mistake in the previous video when we tried to compute the depth of the camera to the view plane. Let's redraw this. I said the ratio 1/z, this is equal to the sine of this angle is 30, so this was equal to the sine of 30 degrees. That is totally false. 1/z obviously in this case is the tangent of whatever this angle is, and in this case it's 30 degrees, so it's 30. And z will equal to 1 over tangent 30 degrees for the FOV to be 60 degrees. And tangent of 30 is square root, 1 over square root of 33. So the result will really be square root of 3. And the square root of 3 can be approximated with 1.73. So use this for the camera depth instead of what we had, which is 2. So this is the more correct one we want to use if you want the FOV to be approximately 60 degrees. Just really quickly get that correction. And remember, I give an exercise to what to do with the stretching artifact. Remember, our screen was because the screen was not a perfect square, but we're assuming a perfect square in our own, normalized space. We're kind of mapping a perfect square image onto a, stretched for a stretched screen. So as you can see, there will be a relatively equal amount of pixels mapped along the x dimension, but for the on the y dimension, but for the x dimension, pixels are going to be stretched, so each pixel will be a little wider than they're supposed to be. To fix this unequal distribution, there's a very simple fix. So this is our square root viewplane. Perfect square viewplane. All we have to do is to transform it into a viewplane that has the same width, the same height to width ratio. Therefore, all the pixels would be mapped to the screen in the distribution that we really want it to be. Now remember, on perfect square, I have everything to be 2. Now all we have to do is, after we've obtained the normalized values, we just have to multiply the ratio of width over height. Width is this and height is this. That way we can obtain the width of the new viewplane in such a way that the ratio of, in this case, height is 2, width is 2 times width over height. Let me just add a little notation so that we know they're different. And if we divide these two terms, so we find this is called the aspect ratio of the screen. So we find the aspect ratio of the view plane, the abstract mathematical view plane. This is just going to be 2 over 2 times width over height, and this will turn into height over width. So as long as these two aspect ratios are equal to each other, the pixels are going to be mapped perfectly without any stretching artifacts. So let me just do that really quickly. Let me get on Shader Toy. Graphics from scratch. I have shader at the description. So I've fixed the 1.73 already. So all that's left to do is, fix the stretch artifact. All we have to do is take out the x term of the UV. Remember what I said. We're going to multiply this range by width over height. Now, because the center of the number line is 0, if you just multiply the number, it's going to stretch along both dimensions, automatically. So all we're going to do is the aspect ratio is the resolution, the x of the resolution divided by the y of that resolution, and this is the actual correct aspect ratio. And if you look at the very right, the image will actually match the reference image. It should be really obvious that this is a way more natural image than what we had, because let me just comment it out. Do a comparison. This is obviously, it looks like it's not real, but this is the right proportion. Okay, so let me just save it. So this one-liner is the solution to our problem. It's very easy.